Morning, all. Gary Bever Jr. here. Audio looks like it's going okay. So join, let me know if there's any issues. And what I'll do today, it'll be a short one. I'll actually cover something that was on the roster for a while, reading some oscillations in classical dynamics. So the idea is that in my foundations class, we'll review the foundations of physics. One of the things we're starting to study now is oscillations. So I knew this was coming up, so I planned on throwing this in when the time was right and the topic has just come up. Let's take a look and read a little bit of this and get a bit of a basis of oscillations. And I'll be back for a longer video either next week or sometime during the week. Introduction. And again, this is classical dynamics. Chapter 3. We begin by considering the oscillatory motion of a particle constrained to move in one dimension. We assume that a position of stable equilibrium exists for a particle, and we designate this point as the origin. If the particle is displaced from the origin, in either direction, a certain force tends to restore the particle to its original position. An example is an atom in a long molecular chain. The restoring force is, in general, some complicated function of the displacement and perhaps of the particle's velocity, or even some higher time derivative of the position coordinate. We consider here only cases in which the restoring force F is a function only of the displacement. So here, F is only a function of X rather than other things. We assume that the function F of X that describes the restoring force possesses continuous derivatives of all orders, so that the function can be expanded in the Taylor series. We have a nice Taylor series for us. And the sub O means it's expanding at the origin, so around 0. And the 3 exclamation point is called the factorial. That's 3 times 2 times 1. I like how they write this. Usually I write it with a prime on the exponents here. So it's always the exponential, the variable that we're talking about to the power that we're discussing. So this was the variable to the 0th power. So anything to the 0th power is 1. And also the function to the nth derivative, whatever, factor or item that is. And it starts counting from 0, then 1, 2, and so on and so forth. So pretty straightforward. And if you have any questions, drop one in the live chat or in the comments later. But F0 is the value of fx at the origin, x equals 0. And dnf over dnx, O is the value of the nth derivative at the origin. So you take the derivative, then plug in the origin. Because the origin is defined to be the equilibrium point, F0 must vanish because otherwise the particle will move away from an equilibrium point and not return. In other words, if the particle is at equilibrium, if there's a force acting on it, F equals ma, then it'll accelerate. Let me actually adjust my scrolling text really fast. Then we continue our attention to displacements of the particle that are sufficiently small, we can normally neglect all the terms involving x squared and higher powers of x. We have, therefore, the approximate relation. So basically this formula for the displacement, a small displacement, actually comes from the Taylor series. So this is 0 because there's no force at the origin because it'll be pushed out the origin. And these will be so small that we could ignore them. So we basically taken this right here. And it seems we're calling this force here K or negative K. We'll see how that goes. We have substituted K. Yep, that is correct. K equals negative df dx naught. So that means that the first derivative of the function at the origin is, well, with a negative in front, is what we consider the, what would we say, the qualification. Derivative is negative, therefore K is positive. Because the restoring force is always directed towards equilibrium, the origin, because it wants to go back to the point where there's no force acting upon it. So the farther away you get from the equilibrium, the more force is acting on this oscillatory thing. The derivative df dx at the origin is negative. And therefore K is a positive constant. These negatives always trip me up a little bit. Only the first power of the displacement occurs at f of x, so the restoring force in this approximation is a linear force. Only the first power of the displacement occurs in f of x, so the restoring force in this approximation is a linear force. Right? Physical systems described in terms of the equation 3.2 obey Hooke's law. One of the classes of physical processes that can be treated by applying Hooke's law is that involving elastic deformations. As long as the displacements are small and the elastic limits are not exceeded, like the spring is not bent permanently, a linear restoring force can be used for problems of stretched springs, elastic springs, bending beams, and the like. Like, for instance, a beam that's flat and made to vibrate up and down. But we must emphasize that such calculations are only approximate because essentially every real restoring force in nature is more complicated than the simple Hooke's law force. Linear forces are only useful approximations, and their validity is limited to cases in which the amplitudes of the oscillations are small. Damped oscillations, usually resulting from friction, are almost always the type of oscillations that occur in nature. We learned in this chapter how to design an efficiently damped system. This damping of the oscillations may be counteracted if some mechanism supplies the system with energy from an external source at a rate equal to that absorbed by the damping mechanism. Motions of this type are called driven or forced oscillations. So you have something slowing down the oscillation that's damped, something that's driving the oscillation that's driven. Normally sinusoidal, like a sine wave, they have important applications in mechanical vibrations as well as electrical systems. Professor was talking about how, remember the device, something, I started to say brakes. Yeah, he was talking about brakes, not brake shocks, how the shocks in a car's tire or struts that's stopping the car from just hitting a bump in the road and having a sharp jolt. These types of laws of oscillations are what apply there. So basically you have a damped oscillator because like these shocks have some kind of fluid up in there, and of course it's in air, but the air is not as damping as the fluid. And he spoke about, which we'll get into eventually, how the different variables that, so if I was to scroll a little bit, I know I saw the equation. Well, I guess it's going to be a little bit till we get to that equation. But suffice it to say that the full equation, the differential equation that governs these oscillations, like right now we're looking at f of x equals negative kx. You can have the first derivative and the second derivative taken into account when you take into account damping, for instance. And the force that's driving it will be a separate force. And these variables that are in front of the differential parts of the equation, you know, if one is bigger than the other, it'll determine how strongly the damping affects itself. So basically you use these equations to determine how much shock to put into our wheels so that we bounce the appropriate amount. You know, we don't sit there bouncing forever. If we hit a bump, we bounce just once, right? And then we settle back down. So it's possible to design these things improperly, to improperly take into account oscillations. And either you don't bounce at all, you just boom, and you feel the jolt, or you just keep bouncing over and over and over again. And this deals with, you know, how you damp your oscillations. Do you have critical damping and things like that, which we'll get into eventually. Applications in, as well as electrical systems. So we spoke about the other day LRC circuits, where basically you have a circuit and the resistor is basically the damping, and there's a solenoid that's up in the circuit is causing the driver, and these systems act just like having a damped spring. So it's pretty cool. The extensive discussion of linear oscillatory systems is warranted by the great importance of oscillatory phenomena in many areas of physics and engineering. It is frequently permissible to use the linear approximation in the analysis of such systems. The usefulness of these analyses is due in large measure to the fact that we can usually use analytical methods. When we look more carefully at physical systems, we find that a large number of them are nonlinear in general. We discuss nonlinear systems in chapter 4. So I'll find the equation I was talking about. So we'll skip a bit. And then I may close out. Like I said, it'll be a short one today. I passed it. I think I passed it. So this book, apparently every time I change pages, it scrolls what I don't necessarily want it to be. We'll get through it. So this is on the simple. So this is solving these diagrams. Okay, so now we get to the damp one here. So here we go. We're starting to get there. So the K will be our, you know, our normal K. And D, resisting. And this is what I was looking at right here. So the omega naught squared is basically the fault angular frequency. And B puts a damping on that oscillation. And how these things relate to each other will determine the nature of the oscillation, whether our omega naught squared is greater than the damping, so it could move a bit more freely, or if the damping part is really big, which will really slow down the oscillation. So it's pretty interesting. Even when we get to things like when you have your door that's has a little stopper on it where it doesn't just hit the wall, it slows it down and you can hit a little uh, pressure release in it. So all of these things are determined by this type of physics. So like I said, I'll keep it short this week. See somebody join. Thank you for joining. And be sure to let me know in chat if you have any questions, if you have anything in particular you want me to cover. And I'll see what I'll cover next week. I'll probably do some things during the week as well on some classical mechanics with some more oscillations and a few other things. So look for me then. I'll see y'all next time. Thanks who joined. Y'all have a good evening.